Hello student, to the Foundation of Classical Electrodynamics course. Under module 2, today we have lecture number 34 where we discuss the multipole expansion. Today we have okay, so our topic today is multipole expansion. So we have already discussed the dipole, so let us quickly recap. So if we have two equal and opposite charge q1 and minus q separated by a distance say d, then at some point we can find the potential or the electric field due to this dipole. If this is r plus, this is r minus, and from here we have r, say this angle is theta. So this is the P where we try to find out the potential, and if I calculate, so this calculation is already done, the potential due to the dipole at point r comes up to be 1 by 4 pi epsilon 0, and then q d cos theta divided by r square. That is a very important thing. Now here the potential goes to, so what we find here, potential goes to goes like one by r square form. This is the way the potential changes. Now if we look carefully for other cases like a monopole, a single charge either plus or minus, this is called a monopole. The potential phi r varies like 1 by r. So now we have dipole where instead of having one charge you have two equal and opposite charge, say minus and plus, and this is called dipole. The potential now varies as 1 by r square, right. Now we can extend these to other kind of charge system, like if I have 4 charge points having say plus and then minus plus, this kind of charge distribution we call it quadrupole. And here the potential will vary as 1 by r cube. Also we can have like a structure with the charge particle sitting here 1, 2, 3, 4, 5, 6, 7, and another charge is sitting here 8. So, this kind of system is, say, this is minus, this is plus, this is minus, this is plus, this is minus, this is plus, this is minus, this is plus. This is the charge distribution we can have, and this is called octopole. Where the potential changes like r to the power 4. So, different kind of charge system you can consider, and this is the way the charge is the potential is changing. Now, the next thing is we will systematically find out the potential of a arbitrary charge distribution, and we later we find that it can be the contribution of monopole, dipole, quadrupole, octupole, and so on. This is the way we can. So, I have a arbitrary charge distribution here. So, let me do that. So, now we will do the systematic expansion of a systematic expansion of an arbitrary localized charge distribution. So, that thing, so I should have a region where we have charge distributed and take a small piece of that, and our goal is to find out what is the potential for this small piece at some point P here, and suppose I have a origin here at some point. The location from the origin to this small portion is, say, r prime, vector r prime, and this location of this is r, curly r, and from the origin to the point P, from the origin to the point P, say this is my point P, this is vector r. So, we know that, I mean, this is a well known problem. Suppose this angle is given and this is, say, theta prime, and this problem is a well known problem because we already know what is the potential for this charge distribution at point P, and that is nothing but 1 by 4 pi epsilon 0 integration of the charge density here, which is rho r prime dv prime divided by the distance from here to here, which is r, right. Now, this vector r is vector r minus r prime, curly r is vector r minus r prime. what is the magnitude of this quantity, or if I want to find out the dot product, so it should be r minus r prime dot r minus r prime, which simply gives us r square plus r prime square minus 2 r prime angle between these two, which is cos theta prime. Okay. So, r square I can write as r square taking common 1 then plus r prime divided by r square of that minus of 2 of r prime divided by r and cos theta prime. I just take r square common and we are going to get this one. Now, let us consider this part to be epsilon, which is essentially r prime divided by r, then r prime divided by r minus 2 of cos theta prime. I just write it as epsilon to make life simple. Then my r will be simply r 1 plus epsilon to the power half. Okay. So, now I just need to expand this r. This technique we already used to calculate this when we are calculating the potential of a dipole. So, the same technique we are going to use that. So, 1 by r is simply 1 divided by r and 1 plus epsilon then to the power minus half, and I can make a binomial expansion like 1 by r and then 1 minus half of epsilon plus 3 by 8 epsilon square and then minus 5 by 16 epsilon cube and plus so on. Okay, this is the expansion we can have. Now, I can put the value of the epsilon here, and if I do that, then I should get some terms which is very interesting. Why it is interesting, we are going to discuss. So, let me write it. So, 1 by r was my first term, and then I write 1 minus, this is half into epsilon. Half into epsilon I just write like half, and epsilon I already know, this is r prime divided by r and then multiplied by r prime divided by r minus 2 of cos of theta prime. That is my first term. What is my second term? I just write it here, plus 3 by 8, and my second term is the square of that. So, r prime divided by r square of it and r prime divided by r minus 2 of cos theta prime and square of that. What is my next term? It is minus of 5 by 16 and cube of that. So, I have r prime divided by r cube and then r prime divided by r minus 2 of cos theta prime and then whole cube of that. and so on and so on. Okay. So, now in the next step what I do is very important, that I gather the term based with the power of cos theta. So, if I do that, then 1 divided by curly r in the left hand side, it should be 1 by r, and then I have a bracket, the first term is 1, then I have r prime divided by r, and the cos term is here. So, first order is cos theta. So, I should have simply cos theta prime. Then I gather all the term associated with cos squared theta, and if I do, then I should have a term like plus r square r prime divided by r square of that, because the cos squared theta is sitting here. So, you have we have like this. No, I just gather all the order of this r, the separate out the order of r divided by r prime, the power of r divided by r prime. Let us do that. So, here we have cube. So, when I make a cos theta, then its power is 1, then I have a square here, and then I have a square here also. So, I need to adjust this. So, if I take r minus r square, then the rest of the term should be, say, there is a 3 there. So, I should have 3 cos square theta prime minus 1 with a half term, and if I gather the cube term, cube of r minus r prime divided by r, this quantity. So, plus r prime divided by r, next term is associated with q, and if I take a common, then it should be 5 cos s cube theta prime minus 3 of cos theta prime and divided by 2, and so on. Okay. So, what I do, let me explain once again. So, I have this expansion, and after having the expansion, now I am gathering all the term which is the power of r ratio r prime divided by r. So, if r prime divided r is x, so I first take the term x, then the term associated with x square, then the term associated with x s cube, and so on. Okay. So, now after having all this term, let us now do something else, because this term we need to identify why this term is there. This is important term. So, this is a note. The note is the coefficient of different power, whatever we are getting here, the coefficient of different power of different power of r prime divided by r, very special term which is called the Legendre polynomials. So, what is Legendre polynomial? Let us quickly understand. So, Legendre polynomial is nothing but the set of parameters. So, let me write it here. So, Legendre polynomials are in principle are a set of polynomials set of polynomial functions rather which are solution of the following differential equation. So, we have a specific differential equation and whose solutions are basically. So, let me write down the differential equation, very famous one, 1 minus x square d2y dx square minus 2 of x dy dx plus L into L plus 1 y equal to 0. This is a very famous differential equation. In many branches of the physics you will going to encounter this equation, and the solution here y as a function of x, and we write this solution like P L x. These are the set of solutions. And P of L means different values. So, L here is 0, 1, 2, 3 etc. L here is 0, 1, 2 etc. integers. So, I have P 0 x as 1, I have P 1 x as x, I have P 2 x as half of 3 x square minus 1, I have P 3 x as half of 5 x cube minus 3 x, and then I have P 4 x would be something like 1 divided by 8, then 35 x to the power 4 minus 30 x square plus 3 and so on. In general, if I write what is PL, so it will be like this. So, PL, which is a function of x, can simply be written as 1 divided by 2 L factorial L, and then dx to the power L dl, and the function x to the power x square minus 1 to the power L. So, if you now put the value of L and try to find out what is PL exploiting this, you will get all these results. Okay, now what is, why I am doing that? Because now if you carefully look with these expressions that we have here, the coefficients especially, then let me just highlight this coefficient here. So, this is the first coefficient I am having, then I am having the second coefficient, which is this one from here to here, and this is the third coefficient, which is exactly the same that value we are having here. This is the coefficient, this is the coefficient, this is the coefficient. So, these are matching, this. So, all coefficients that we are getting are essentially the Legendre polynomials of different orders. So, I can write my 1 by r after having the knowledge. I can now write the term 1 divided by r as 1 by r, then summation L can goes to 0 to infinity, and the coefficients of r divided by r prime divided by r is important, and then these are the Legendre polynomials with the argument cos theta. So, if I replace x to cos theta here, if I replace x to cos theta, then I will simply go back and check, and we will find that I will going to get this one. Cos theta means theta prime, because everything is in prime. So, I should put a prime here. Okay. So, that I simplify. So, I can write it as L equal to 0 to infinity. So, okay, here I should have L, because this order is also changing. So, r prime to the power L divided by r L plus 1 and the Legendre polynomials. This is the way you can expand your 1 by r term. This is quite exciting, that you just expand 1 by r term polynomial in a this way, and you will going to get. So, what should be the form of the potential then? What should be the form of the potential? The form of the potential phi r, let me write it once again, it is 1 divided by 4 pi epsilon naught, and then integration of rho r prime dv prime divided by r. Now, this r 1 by r, whatever the 1 by r I have, I just write it here in this way, 1 divided by 4 pi epsilon 0, and then I can have the summation sign here, where L goes to 0 to infinity, and 1 by r I write like 1 divided by r L plus 1, this term, which can I take inside outside the integral, because the integral is over prime, and then integration r prime whole to the power L, and then P L cos theta prime, then rho is there already, which is a function of r prime, and dv prime over the volume integral V. So, I can have a series here, the potential can be defined, can be expanded in terms of some series, and if I expand this, I will get the term 1 by 1. So, let us do that, 1 by 4 pi epsilon 0, and the first term is 1 by r. By taking L equal to 0, I have rho r prime and dv prime. This is my first term. What is my second term? 1 by r square, L equal to 1, 1 by r square, integration of r prime and cos theta prime rho r prime dv prime. This is my second. Here I use the PL. So, this value is associated to PL 0, L equal to 0 with cos theta argument, and this value is associated to P L equal to 1 cos theta, which is simply cos theta. So, that value is here, and so on. We have then we have then we have 1 divided by plus 1 divided by r cube, then r prime, then r prime square, then half of 3 cos square theta prime minus 1, and then rho r prime dv prime, and so on. Well, this term again is P L equal to 2 cos theta argument. So, that value is this one from here to here. From here to here, this is this one, and this is 1. Okay. So, now I can write these things individually, like phi 1 r plus phi 2 r. So, entire potential is divided into different phi's, where these different phi's, phi 1, phi 2, phi 3 corresponds to the values like this. So, what is my phi 1 here? If I look carefully, it is 1 divided by 4 pi epsilon 0 integration of rho r prime dv prime divided by r. This is a known term, right? So, this term is nothing but potential due to the monopole, contribution of the potential What about phi 2 here, which is a function of r, again a function of r. So, that is 1 divided by 4 pi epsilon 0, and then 1 by r square integration of r prime, and then cos theta prime rho r prime dv prime. I can manipulate, I can write this in a different way, 1 by epsilon 0, then 1 by r, and this cos theta I can write it as r prime cos theta, this term cos theta prime I can write it as r prime vector dot r unit vector. As per the figure, if you look carefully in this figure, whatever the figure I draw, so this is theta prime. So, r prime dot unit vector r is simply r prime cos theta. So, that I replace here in this equation. So, this is r square and r unit vector dot integration of r prime rho r prime dv prime. Now, this is a known term again, and when we discuss the dipole moment, then we mention that integration, the dipole moment is essentially integration r prime rho r prime dv prime. So, this is nothing but the dipole moment. So, this is the dipole moment. So, once we recognize this is a dipole moment, my phi 2 can be written very nicely, and that is simply 1 divided by 4 pi epsilon 0, and then this is dipole moment P. So, I should have P dot unit vector r divided by r square. So, this is nothing but the potential due to dipole. Okay, so now I believe you can understand that when I divide this phi systematically, I can have the contribution here, which is the contribution for monopole. I have a contribution here which is due to dipole. I have another contribution which is, if I do the similar thing, I only did for two cases, phi 1 and phi 2, but in principle I can also find out what is phi 3, and if you do that you will find that this is for quadrupole and so on. So, that means when for a distribution of charge, when I have a distribution of charge, then whatever the potential it is exerting on some point r, that is the summation of, that it seems it is a summation of all the charge distribution here, and this charge distribution is systematically we find that it is a contribution of the monopole here, it is a contribution of the dipole here, it is a contribution of the quadrupole here, and so on. If I add all together, then I will have the entire contribution here due to this charge distribution. But a systematic, when we systematically expand this term, we find the components of the monopole, we find the component of the dipole, we find the component of the quadrupole, and so on. So, today I do not have much time. So, in the next class I will try to understand more about the dipole moment and how to calculate the dipole moment and monopole moment. This term, the first term is called the monopole moment. The monopole moment is rho r dv. This term is called the monopole moment. What is the meaning of monopole moment? From that you can readily understand that it is nothing but the total charge q. So, total charge q is your monopole moment, and so on. So, I would like to conclude here today, and in the next class I am going to discuss about this, how the dipole terms will be there and what should be the consequence of the dipole term, how you calculate the dipole term for a distribution of the charge, and dipole moment calculation for different distribution of the charge, etc. So, thank you for your attention, and see you in the next class where we discuss all these issues.